Hey everybody, welcome to another physics video. Thrasher here. We are talking about really the culmination of a lot of the physics that we've been going over in the last set of videos to understand the idea of how we stay safe. Whether it's by our actions or things that we design, the impulse concept, building off of our last video, the impulse equation, explains basically every single thing humans have designed or thought about when it comes to keeping ourselves safe. This is one of my top 5 physics topics. I love, of course, that physics applies to our daily lives. Here you're going to see in a way that you've probably never really thought of, probably overlooked your whole life. There is a single core physics concept that explains safety. You don't believe me? Oh man, you gotta stick around, okay? So, starting ourselves off, we are still in the realm of looking at collisions, okay? Whenever there's a collision, there is a force involved, always, kind of by definition. If you have one or more things slamming into each other, those things are in contact, they are applying forces, okay? So, there's always forces. If you have objects colliding, well, objects, basically by definition, they're gonna have mass associated with them. They also have velocity. If you have objects with zero velocity, they can't really collide. So there must be velocity from one or both objects. And time. A lot of times you think of collisions happening instantaneously or very quickly, but all collisions take time. If we had a slow enough or a high-speed video, we could see, while it might be a fraction of a second, it takes time when my fist, say, collides with the palm of my other hand. This is a slowed down GIF showing small but still an amount of time of this car. This car was being pulled. This was a crash test. This was not an actual test, thank goodness. But scientists pulled this car at a very high speed and it slammed into this barrier. And it took some time, not a lot, but some time for that car to come to a rest. So all these things are involved in a collision. And team, we learned in our last video an equation called the impulse equation. And that equation has all those things I just mentioned. Whenever you have a collision, there is a force. An object or objects have mass, they have velocity. Usually those objects' velocities are changing, at least in one regard or another. And all that takes time. So what we're talking about is based on this equation, but we're not going to do any math, at least not direct plug and chug math, okay? First, for this equation, I'm going to rewrite it. Remember, m times v, that is momentum. So maybe you could say I'm a little bit lazy. Instead of writing m and v, now I'm actually just going to use p for momentum. So exact same equation. Force times time causes a change in momentum. If I didn't want to write it with symbols, I could write it in words. Remember, this is just describing what this means in math. When you're subtracting an initial value from a final value, what you're looking at is the difference. That's what subtraction means, the difference. We're looking at the change. So f times t is equal. That's what this is right here, the change in momentum. Last thing I'm going to show you. We actually saw this symbol, I believe, once before in my video about acceleration. But this symbol right here, this is Greek letter delta. In math and in physics, this symbol represents change. So these two things are the same thing. I am again saying force multiplied by time is equal to, you read this as the change in momentum. And I've written it like this just because it's shorter. It's easier to write than all these other things. But it's the exact same equation. Force multiplied by time equals a change in momentum, okay? All right. The next thing I'm going to show before we move on to my next slide, my next page, is maybe going to seem silly, but it's kind of the crucial point of the whole rest of this topic. Let's remember something about math, okay? Let's say I take two numbers and I multiply them together. That's all I'm doing. I'm taking number A, I'm going to multiply it by number B, and obviously when I multiply numbers, I'm going to get some number, okay? Now what I've done here is I've kept what the numbers are going to equal the same. So all the numbers that are going to be multiplied, I'm saying they all equal 100. I just made up a number, but just stay with me. So there's multiple ways to multiply two numbers to get 100. Of course, I could do 100 times 1, that equals 100. Or I could do 50 multiplied by 2, that equals 100. Or 25 times 4, that equals 100. All of these are different combos. Now, the way I organize this is important. Notice, I have kind of the number on the left and the number on the right. Left and right, left and right. Here, I'm slowly decreasing the number on the left. I started with 100, and then I made it 50, and then I made it 25. If I make the number on the left smaller and smaller and smaller, but I'm always keeping the product, the result, the same. What is going to be happening to the number on the right? Does it get bigger? Does it get smaller? Or does it stay the same? It gets bigger, and hopefully that makes sense. If I'm always getting 100, I always have to balance the two things I'm multiplying to get that same number, that 100. So if I start with a big number on the left, the number on the right can be smaller. But if I make the number on the left smaller and smaller and smaller, but I still have to equal 100, I better ramp up what the number is on the right-hand side. So if one of these numbers gets smaller, the other number has to get bigger, and vice versa. That's the big idea. If I'm equaling the same thing, if one side of these numbers gets smaller, the other has to get bigger, okay? Okay, put a pin in that. My ultimate question for today is this scenario, team. Let's say I have two eggs. Let's say they're identical, the same size. Let's say I'm holding both eggs the same distance from the floor, and I drop them. I drop both eggs. Hopefully it's not surprising, this scenario. If one of those eggs lands on a nice soft pillow, like that you sleep on, there's a good chance that egg is going to survive. But if another egg that was identical doesn't land on the pillow, instead hits the hard ground, it breaks. Why? What is the physics of this? Why is it that an otherwise identical egg survives when it lands on a pillow versus when it hits the hard floor? That's what we're trying to answer, and we're going to use that impulse equation to show it. Again, this is the impulse equation. Force times time equals the change in momentum. Here's what's important for this picture. I have the same eggs, so they have the same mass. If I drop them from the same height, they're going to be going at the same speed as they're falling down, okay? They're going to have the same speed right before they collide. And look at this picture. Both of these eggs are at rest. Both of these eggs have zero speed, zero momentum. So if I have the same eggs drop from the same height, they're going to have the same speed right before they collide. They're both at rest. Both of these eggs will have the same change in momentum. So like I showed you before, I can kind of keep this number on the right the same, okay? Now, impulse, just like I showed you with that math example, it's when two numbers are multiplied, force and time. Well, can you look at this and explain why the egg that hits the pillow is going to be safer? It survives. There's less force that is being applied on this egg. That's why this egg doesn't break. The egg doesn't break because the force that's acting on it is smaller. Why? Based on this impulse equation. Notice what happens for similar situations that have the same change in momentum. If one of the scenario requires a bigger time, notice, right here I have let's just pretend 4 seconds. I know it doesn't take 4 seconds for the egg to hit the pillow, but we're just kind of pretending. If the time is relatively larger, the force has to be smaller. That's the idea. That's how we keep these eggs safe. On the left-hand side, what happens? When the egg hits the ground, bam! It happens in a very small amount of time. If the amount of time the collision takes is small, the force, comparatively, has to be larger. But when the egg hits the pillow, let's imagine slow motion hitting that pillow. What does the pillow do? It compresses. It absorbs. The pillow moves down. All of that increases the time. The pillow makes the time of the collision larger. And if the time is larger, what must be true about the force? It has to be smaller. I love this diagram. I know there's no numbers plugged in, but it shows you, again, similar eggs, similar scenario, so the same change in momentum. But if one of them has a small time, that's this guy right here, a small time leads to a larger force. In the right-hand scenario, exact same change in momentum, but the pillow increases the time. It's a little counterintuitive, team. If I'm telling you you're going to collide with something, do you want that collision to take a big time or a small time? You might be like, oh man, I don't want to be in a collision. I don't want to be in like a car crash. I want that time to be very small. No, no, no. You want the time to be as big as possible because just kind of the rules of math, if the time takes more and more, if it's bigger and bigger, the force has to be less and less. That's the idea. For the same change in momentum, if the change in time is small, you have a bigger applied force. That's this thing right here. If instead you use something that increases the time before the egg comes to a stop, the force has to be smaller. Bigger time, less force. That's our mantra. When time is big, the force is small based on this impulse equation. Same thing is true for cars, everybody. Modern cars, when they get into an accident, they are designed to be obliterated. Again, maybe that's counterintuitive. The bumper, the front bumper of your car has this thing called a crumple zone. It is designed to be squashed. Look at this picture. This car is totaled totally on purpose. Because when a car collides and that front bumper crumples and bends and twists and warps, all of that takes time. More time, less force. You want the collision to take as much time as possible because that means there's going to be less force applied. Let's look at some other examples. I love looking at examples that you may have encountered or at least you're familiar with. When you catch a football, okay? What are you taught when you catch a football? If you've ever experienced this, do you hold your hands straight out rigid and just when it slams into your hands? No. You're taught to catch a ball, if you're a receiver, to cradle the ball into your chest. You let it make contact, and then you bring it in like this. If you're looking at my webcam, you go like this. Why? That increases the time. You cradling the ball in makes the time bigger, so the force on your hands is smaller, less likely that the ball is going to bounce out of your hand. It's not just like American football. If you play soccer, same thing. If someone kicks you a hard pass, usually you don't just stick out your leg and try to jab the ball. You cradle the ball to a stop with your foot, with your ankle. That cradling to a stop, this motion, bringing it in, increases the time, so less force, more control. Modern football helmets and padding, they're made of foam. The foam is designed to bend and twist and crumple and compress. All of that, everybody, takes time. Since that time is extended, the force has to be smaller, in this case on maybe a football player's head. That's how we design good football helmets, okay? Few more examples. Sorry to get a little morbid, but if you are in a car crash, if you don't have airbags, if your head hits the steering wheel, that steering column is very hard. It applies a force in microseconds. If the time to stop your head is teeny tiny, the force that is applied to you is very big. It's going to break your nose and bones in your faces, or I'm sorry, maybe even worse. So why do we use airbags? Airbags are not comfortable, but airbags increase the time it takes to stop your head or your body, whatever hits them. That increase in time decreases the force. You're probably going to walk away injured, but probably alive because it will have less force applied. So what we want? We want more time. Even if you're a gymnast, obviously like there's the padding for gymnasts, and that's like the helmet here that compresses and increases the time, decreases the force. But even like their high bars give a little bit. One reason for that is when they're doing a jump or a trick and they release and then they grab onto the bar bends. So the collision between the gymnast's hands and the bar takes a little more time because the bar bends. That decreases the force. It's less jarring. It's less impact on the gymnast's hands. Even when you're just jumping off of something. I'm sorry, I'm going to tell you a silly story about me. When I was a kid, I want to say kindergarten or first grade, I loved like climbing up the monkey bars and jumping off. Why? I don't know. I was a dumb 7-year-old, but I really liked climbing up on top of things and then jumping off. And my aunt, my cousins were my same age, so they went to the same school as me. So my aunt was at school. She saw me jumping off of the monkey bars and she told me something. And I remember this distinctly all these years later. My aunt told me, hey, make sure you bend your knees when you land. She had no idea probably that she was giving me some physics-based advice. When you jump and you land, you don't want to land with your knees locked. Oh my gosh, that's going to hurt. Instead, you bend your knees when you land. Why? bending your knees increases the time that you are colliding. This is a type of collision. You collide with the ground. When you increase the time, you decrease the force. That's the ball game, everybody. Notice, I'm almost done with this video. I know this one's maybe a little longer than average. Notice what word I have never said. There's a game called Danger Word where you got to kind of play charades, get people to say a word, but you don't want them to say another word. The danger word, nowhere in this video have I said soft. Don't tell me, especially if you're in my class and you're going to take one of my exams, don't tell me the reason why we have airbags is because they're soft. There's no physics in that explanation. The explanation is this. We are using the impulse equation and we're increasing the time, and we're using material that increases the time, or techniques that increase the time. That's going to decrease the force. So don't just say, oh yeah, it's safe because it's soft. That's not physics. My last little bit, okay? Something to highlight. The argument we've been making has been assuming we're using the same change in momentum. Remember, from the very start of this video, I had this math example. My numbers were always equaling 100. We're always looking at the same change, meaning I'm looking at similar objects. We were talking about identical eggs going about the same speed before impact and then coming to a stop. We're comparing similar situations where the key difference is the time. We're increasing, we're slowing down, we're making the time to stop bigger. I have some students who walk away from this video thinking, well, okay, so I guess as long as I have a pillow, the egg will be safe. And they think that they could take an egg, maybe go all the way up the Empire State Building and drop an egg and expect the pillow, or the egg, I should say, to survive. They're like, hey, Thrasher, I have a pillow. How come it doesn't work? And of course it's not going to work here, because in this case, this egg is going to be moving a lot faster. It's going to have a different change in momentum. This is comparing apples to oranges, okay? So we're talking about similar scenarios, car crashes with airbags or not airbags, okay? Catching a football, same football, either arm stiff or cradling, okay? We're comparing similar scenarios here. We're not comparing totally different things. In fact, if you're in my own class, this is probably something you want to have in the back of your mind. This is the key kind of qualifier. Our whole argument is based on this idea. We're comparing objects that have similar or the same change in momentum. If this is true, if we have identical situations, then making the time bigger makes the force smaller. Okay? Thanks a lot, everybody. Again, I love this topic because all these things that you experience, you probably never thought about why you do things a certain way or the intrinsic reason why things are safe. You might have thought of the word soft before, but what's the physics? These things are increasing the time of collisions. And according to this equation, when the time is bigger, the force acting on it is going to be less. And when there's less force, you're safer. Okay? That's all I got. Thanks a lot for watching this video. I appreciate it.